In this video, we will see stress and strain diagram for various materials. Here, if you see, we have engineering stress and engineering strain. So now, there are many diagrams for various materials. If you see, first, this particular mild steel, which is low carbon steel, this is the diagram. Now, if we increase the percentage carbon, medium carbon steel, then its yield strength and ultimate strength will increase, but ductility will reduce. So, ductility is the area under the curve, so its ductility will reduce. And if you further increase in high carbon steel, the ductility further reduces, but its yield and ultimate strength will increase. So increasing in percentage carbon, this is the behavior of the stress strain diagram. Now this particular at 140 megapascal pascal is a cast iron. Its ultimate strength is less, much lesser, less than half, and also it's less than yield strength. Its yield strength is also greater than the ultimate strength of cast iron. So cast iron is brittle, its ductility is very poor. And if you see this blue color below the cast iron, it is a hard drawn copper. So if we draw copper by drawing process, it will be having a cold work and it will be having this much strength. And below that there will be aluminum. Its ultimate strength is 300 megapascal. This is not to scale, but if you see this is 300. And if you see the slope of the aluminum and cast iron, then you see the slope of elastic zone is much lesser as compared to cast irons, because the young modulus of cast iron, which is the slope, is 100, and for aluminum it is 69. So this slope represents the young modulus, and for mild steel it is 240 gigapascal, so it is also higher than cast iron. So young modulus is the slope of this curve. So aluminum is 69, but its ultimate strength is 300 megapascal. So this red color is the aluminum. Then annealed copper, if we heat treat it and make copper ductile, then it strength reduces but ductility increases. Now this particular curve is for the rubber. So rubber behaves like this, its strength is much lesser, also it is much elastic. If you unload it, it will again come back to its original position. So if you see here, this blue color is the normal curve for mild steel, but if you see this red, that is the true curve, true stress strain curve. So true stress strain curve is given by force upon actual or instantaneous area, whereas engineering stress is given by P upon initial area. So this blue color is drawn. Initial area is much bigger than instantaneous in this zone. So that's why this curve will never have a slope in this direction, negative direction. So it is always positive and it's always increasing because the cross section is reducing in tensile test. So this is the true nature of the stress strain curve. Sigma t is k epsilon t whole raised to n. This is a power law, or Holloman law. It is also called a Holloman law. We will discuss in further lectures. Now if you see this particular point here, I have drawn it like this is the yield strength of this particular material, medium low carbon steel, which is mild steel. Now if you see here, if we load up to this point and deform it plastically, means do a cold work here, then it's after releasing the load, it will come to this point. So this will be the permanent deformation. And now if we again load the same material, then it will start following this nature. This both the slope will be same, but it will trace this path, and its new yield point will be this. So yield point will increase if we do the cold work. Now cold work is the plastic deformation. So up to deforming this much, again its new yield point will be this, but it will have negative effect on compressive strength. So its compressive strength will reduce by the amount the yield strength is increased from this point to this point. So this will be the new curve for this material. And now if we load it, its yield point will be this is a new yield point. This is called as Bossinger effect, and it comes at a cost of compressive strength. Now if you see, volume will change in elastic zone, so in this zone there will be change in the volume, because there is no permanent breaking of bonds inside at a molecular or atomic level. So whatever the we are stretching the material in the elastic zone, it will have volume change. And after having entering into the plastic zone, means permanent deformation, there will be change in the volume, because material will break its bonds, its molecular and atomic level bonds will be broken, and its volume will change. Its volume will not change, its bonds will break, and in elastic zone its volume will change. So in plastic deformation there is a no change in the volume. And if you see further here, two graphs. Now here if you see, if we increase the temperature from room temperature 300, 600, 900, then at some point the young modulus value will change, because this slope value will change, initial slope, and its yield strength and ultimate strength will also decrease. So from this curve, if we heat it till 300, its young modulus is not changing because the slope is remaining same, but yield strength and ultimate strength reduces. Now after certain temperature, which is a recrystallization temperature of the material, after recrystallization, if you further increase, its young modulus will change. So it is shown by the slope of this elastic zone curve, and further its yield and ultimate strength will also reduce with the temperature. But this behavior will change if there is a chromium content inside the material. So when there is no chromium, this is the behavior. But where there is a chromium, it is called as blue brittle or dynamic strain regime. So when there is a chromium present inside the material, then it will break the dislocation. In material there are dislocations, and due to high temperature, if you increase the temperature up to 300, it will show the normal behavior as the same. But after 300 degrees celsius, its behavior will change, because chromium will have high mobility inside the material. It will break all the dislocations, and there will be more dislocation, and it will hinder the deformation. And the strength and yield strength, ultimate strength will increase, because there are many dislocation present in the material. And chromium is so mobilized, it will break bigger dislocation to smaller dislocations, and there will be hindrance and resistance in the plastic deformation of the material. So after 300, at 400, its strength will increase further up to 650 degrees celsius. The material strength will increase, and then further increasing, its strength will start reducing. So this effect is because of the chromium presence at the material. 300 to 650 degrees celsius, its strength increases, and in normal material its strength decreases. So this is called as dynamic strain regime. We'll further discuss some more concepts in further videos, and thank you for watching this video. See you in the next video.